Hi, I'm doing Pythagorean theorem proof A. So I just have this on my laptop, but I'm just gonna read it and I'll give like a rundown of my understanding of it and some stuff that I'll do during it. So I know that I'm gonna have like a slide set for it, and I'm gonna have pictures of the triangles up on the slides and such, but I want to draw the original description live with the students so that it's really clear how it's set up. So the description is: consider a right triangle ABC with right angle at C with leg lengths of AB, or of A and B, and hypotenuse of length C. On the extension side BC, pick a point B so that BAD is a right angle. So then I'll have the clear picture on the board, and then for them I would ask them like which triangles that they see and if they can name them for me. So the three triangles that we have are ABC, BAD, and ACD. And I would highlight these in a slide set for the original picture, but then also draw them and orient them all the same way so that it's clear which side lengths correspond for the similarities. So we want to prove that a squared plus b squared equals c squared, and we want to find the area of the triangles to compare them to find this. So in order to find the areas of the triangles, we need to find side lengths DB, DC, and DA. If we orient these triangles the same way, they all look similar, as I said, because they all have a 90-degree angle at ACB, DAB, and DCA. And then also, since DB is collinear with BC, angle ABD equals the angle ABC. So then we can use this to get a triangle similarity proportion. So we have DB is to AB as AB is to BC. And then, so that's DB over AB equals AB over BC. And then with the known side lengths, AB equals C and BC equals B, then we have DB equals C squared divided by B. And then similarly, we have DC is to AC as AC is to BC. So then that's DC over AC equals AC divided by BC. And then with our known side lengths that we plug in, we get DC equals A squared over B. And then similarly, AD is to AB as AC is to BC. And then with our known side lengths that we plug in, we get AD equals AC divided by B. So now I would show the picture of the original triangle with all the side lengths filled in terms of A, B, and C, since we know them all now. And same thing, I would continue to fill in on the board all three separate triangles. I think this would be like a good way to keep them engaged and make it clear with both pictures simultaneously, the original and the slide, and then the three separate triangles on the board. So then moving forward, we'll find the areas, which is equal for triangles equal to 1/2 base times height. So the triangle ACD is equal to 1/2 A squared divided by B times A, which is equal to A cubed divided by 2B. And then the area of triangle ABC is equal to 1/2 AB. And the area of triangle ABD is equal to 1/2 C times AC divided by B, which equals AC squared divided by 2B. This is something that I would have the students do on their own for like 30 seconds to a minute, because I think that once we all have the side lengths, they can do some algebra, and I think that that would keep them engaged, because quick math like that is fun. So and then we would have the picture, and we would have the area of all three triangles and what they're equal to, and then I would be prompting the students to ask like how they think we can move forward from this. But for me, I decided to get the equation that the area of triangle ABD is equal to the area of triangle ACD plus the area of the triangle ABC, since those two little triangles make up the big one. And then if we plug in the known areas that we just found, we have AC squared divided by 2b equals a cubed divided by 2b plus ab divided by 2. And then if we simplify that and get a common denominator on the other side, we have AC squared divided by 2b equals a cubed plus ab squared all over 2b. So then I prompt the students and showcase this equation compared to the Pythagorean theorem equation, and kind of ask them to start thinking about how they think we can get the equations to look the same. So we notice that there's an a in every term in the numerator and a 2b in every term in the denominator, so we would factor out a over 2b. And then if we cancel those on both sides, we would get c squared equals a squared plus b squared. So by triangle similarity, it is true that c squared equals a squared plus b squared for a right triangle with leg lengths AB and hypotenuse length C. Something that's also interesting about that equation is that, I don't know why my light turned off, but the area of the triangles are all like a ratio proportional to the square of their shortest leg. So C is the shortest leg of triangle ABD, and so on. And then throughout my lesson, I kind of explained a little bit of what I'll do throughout, but I want to have the slides be really engaging so that it's really clear, because this is that's like all the different side lengths and letters and triangles and angles can be really confusing when you're just hearing lots of letters. So I don't want to do a lot of speaking. I want it to be a lot of visual stuff to really make it clear for the students, and also giving them some time to do their own computations with like the area formulas. So I'll ask them questions like which leg in triangle ABD corresponds to leg A in triangle ABC, and try to get like those call and response things going. I want to have like the triangles highlighted and have them separated in multiple different versions of the pictures and how they're oriented. And I really want to ask the students like how they think that we can get the area of the triangles to the known Pythagorean theorem equation that we have, just to get them prompting. So yeah, and I also want to wrap it up with a question about like what they notice with the triangles and how they simplify into the square of their shortest length leg, because I think that's interesting. But and then the history of it, I'll kind of state that the method of this proof for the Pythagorean theorem by similar triangles was developed by Euclid, and he proves it in book 1, proposition 47, which was likely around 300 BCE. So yeah, that is my lesson. I feel confident about the math aspect of it. It's been a while since I've worked with triangle similarities, so I guess I'm just wondering if I said enough to show why the triangles are similar and why we can do the proportions that we do. I mean, my explanation of it is like the hypotenuse on triangle ABC corresponds to the hypotenuse on triangle DBA. Just want to make sure that that's enough, I guess. Like enough background for that proof, I guess. But yeah,